This podcast is brought to you by LMU Munich.
So this is part of a research group that's going on since 2008 of the epistemology of the Large Hadron Collider at the University of Wuppertal. And as such interdisciplinary collaborations go, they often find you flat-footed. So here you have a trained mathematical physicist who is approached by real certain particle people who are working for the Atlas detector. And we started to do a discussion group for 1 or 2 years because these were people who weren't so far much into philosophy. And then we got some DFG projects which were running since 2008, etc., etc. And we tried to understand what are interesting philosophical epistemological questions at the LHC, ranging from general philosophical things like what's the ontology or epistemology of the Higgs mechanism, through the Atlas technical report, through, this is one of the projects I was launching, the model dynamics in the Higgs sector. So because there's a plurality of models beyond the standard model, etc. But what I want to talk today are Feynman diagrams. They always fascinated me, especially because I'm very intrigued by action functional and by the Feynman path integral, and of course by pictorial representations. So here's a bunch of Feynman diagrams. Can be different things. Here's a real Feynman diagram where from gluons a Higgs particle is created and then it immediately decays into W's. This is one of the channels where that they have spotted. Here is artist and I would say visual scientist Edward Tufte, who has a whole wall of metal Feynman diagrams. And here's a simulation of a Higgs process. And you see, well, it has something to do with scattering pictures. Well, last year and this year, they give their annual presentation what they found, their signatures, as they call it, and their statistics, when they could declare last year that with 5 sigma, they are sure that the signatures they have seen were not created by anything but what is a good Higgs candidate. Okay? But then they talk to you about, well, what processes are we looking at? So this Higgs could come from gluon fusion, that's this channel, from a vector boson fusion, so you have a WZ from associated product with WZ and with 2 tops. And all of these are signatures. Some of them they can measure better, others they can measure worse. And if you look at the other detector, the CMS, you see that the Feynman diagrams are even more abundant. So here they were telling us what we had till the announcement of the Higgs last year. So that was a top process. And again the channels. And now they are looking into all the single channels. Should I make this a bit higher or the lower? Actually, I think probably this lower. Yeah. Is this in the right direction? Was it the wrong direction?
Too low? Yeah.
That's too low, yeah. Okay, it's a metastable equilibrium. So here you see that they correlated even to the bumps. Here again, and sort of they go into such scattering pictures. Here again, so CMS was presented by an American, sort of 10 Feynman diagrams. So experimental physicists use Feynman diagrams to depict processes. And of course they know that these processes are probabilistic and that the particles are virtual in a quantum mechanical sense, they don't see trajectories there. Yeah, that was when Feynman gave his first presentation in Pocoma in 47 or so. Bohr's first objection, I mean, how can you draw a trajectory of a quantum processes? But what they do for the experimentalist is that they represented a type of process, a whole class of process. Because what they want then from theoreticians is some stuff like, oh, calculated this kind of process up to a certain order. So you have, then on the other hand, the theoreticians will say, yeah, I mean, they are talking about process, but what they want from us is a number, and they really don't care what we do. So we theoreticians, we have, sorry you can't see this, we have this, well, that's a Feynman diagram, this symbolic one here. We have a vertex, and the vertices are associated to propagators, so to Green's functions. Okay. And that's already in the modern setting, so that's not the historical setting, that's current edge. So you have also ghosts, etc. And they warn you, please understand, these Feynman diagrams are purely symbolic. They do not represent particle trajectories. As you might see in them, let's say a bubble chamber photograph, the vertical dimension is time, and the historical spacings do not correspond to physical separation. Each Feynman diagram actually stands for a particular number, which can be calculated using the so-called Feynman rule. So the experimentalists sort of talk in terms of a processes, which seems to be a black box, and then those theoreticians also black box everything, and they exchange numbers, etc. But if you look into the fine print, there's a lot of thing that's pictorial: time, space, like a Minkowski diagram, and the physicists use it for processes. So there's a lot of denial of some representative features in it, and we will go through the history in a minute when we see that these representative features played an important role in the story of Feynman diagram. Because this instrumentalism aside does not explain why they've proven so resilient over 65 years, during which physics changed significantly, and why they had an enormous heuristic potential. Yeah, today we're sort of fine with renormalization and with a lot of quantum field theoretical techniques. We could write down these rules for particle physics propagators, and if you do solid state physics, there are different propagators, etc. And yes, at the beginning in QED, this was also kind of safe. But then Feynman diagrams spread beyond where rules could be justified, especially in the so-called S-matrix program, where people didn't see anymore any connection to perturbation theory. Okay, so physicists today tell you, well, every vertex is a term in a perturbation expansion. Dyson could say that. In between, nobody knew what was going on. So here's what I want to argue for. I don't want to say they represent something out there, but I want to use the modern debate about models to assign to them a representative function that's not kind of connotation theory of truth. So correspondence theory of truth, it represents something out there, because that obviously doesn't work. And I will use these models as mediator approach, because this resilience showed a certain autonomy of the Feynman diagrams, that they are an object of study, an object that gives you confirmation, disconfirmation, you can experiment it with, more in a thought sense than in a real sense. So you can check your hypothesis at it. But the representative features are complex, and you saw already some pictures here. If you have a single Feynman diagram, the theorists often tell, yeah, it's a propagator. And in the experimental discourse, they stand for a certain type of process. And what that means will be my main point. And I will argue, well, it could be a single Feynman diagram that's isomorphic to some mathematical expression. But the interesting point is if we have a collection of basic Feynman graphs, Feynman diagrams, to express an effect or a process. And this is a talk you hear even spectroscopy people talking about. And I remember that's my first interaction with this stuff when I heard Hensch giving a talk at a physics conference sort of 2 decades ago, when he proudly announced, oh, we have measured now the two-loop corrections at the hydrogen atom. And our worst disturbance was the subway down there in Garching. 2 decades ago, oh, the subway didn't go to Garching. Subway ended 5 miles before Garching. And then, of course, your ideal is that the whole infinite expansion, if it makes sense at all, of course, represents the events. And you can work with models. That's important, because the history will be complex. People rebuild all the Feynman diagram techniques. And what I want to talk here about, which isn't that much in the present debate about models, that there's not just model statics that wonders about representation, but also a model dynamics. Okay, the literature is sparse. James Robert Brown held that they do not represent anything, and he basically took up the idea of Bohr. But of course, even Feynman would have agreed, because everybody knew that in-out states are safe, long limit of a scattering process, and that you had a certain local region which you didn't really black box. Why? You could black box it, then you do S-matrix theory, but you start looking into what can happen in there. Yeah, so I think that doesn't work. You can also do some twists with the notion of representation, sort of a non-Goodmanian theory of representation, and say, well, representation is distinct from denotation, so then I don't have the problem that they don't represent something, which in the simple-minded version, of course, they don't represent something because there isn't that process out there, because this is a quantum process. So, but that comes too quickly. There's more in the historical literature with two philosophically well-educated historians who, however, I think leave something for me to do as a philosopher. So this is the book by David Kaiser, Drawing Theories Apart, and by Adrian Wüthrich, The Genesis of Feynman Diagrams. Basic for both the story of Wüthrich, who tells the genesis, and Kaiser, who tells how they spread over the next 20 years or so, is that there's always this dualism between Feynman, who really thought initially in terms of real processes, and the time and space position axis come, of course, from the analogy with Minkowski diagrams. So that was his initial inspiration. He talked about particles, etc., at this POCOMA conference, and everybody said, oh, that was awful. You have no idea about second quantization. You have no idea. You still talk about particles, and you don't know quantum field theory, and Schwinger won the day. And then there was Dyson, who lived in both worlds, also in Schwinger's world, and he was able then to justify all the things that Feynman had done in this presentation, and Dyson even came up with the papers earlier than Feynman. Now, this is not just a historical note, it's interesting that this dualism between this picture process talk, the Feynman perspective, if you wish, and the rule theory approach persists, and sometimes in the history the former dominated, and today we are back into being pretty much rule governed. What did Feynman want to do? Well, he wanted to understand the Dirac equation without these seas of negative entropy, but he allowed particles going back in time. And he thought this was a physical process, namely this quivering electron idea of Schrödinger. He quickly abandoned the search for microscopic justification, took a more abstract approach. So in terms of green functions, where the propagation of a Green's function is no longer a classical trajectory, and that what is really here, the line, then corresponds to a lot of self-effects, autocorrections, etc. Okay, here in the second sense, then the Feynman diagram stands for more processes to which we just attach self-interactions. Why could he do that? Well, path integral approach. And a path integral is a wonderful thing because it doesn't have any microscopic dynamics. It's an integral principle that goes from here to there. That's a funny depiction of your life as a path integral. So all your possible paths in your life. And you have a Lagrangian picture where any elementary particle physics starts today. So our practitioners basically call a model or a theory, well, give me a Lagrangian. You can buy the standard model on a cup at CERN. They don't have the cups for all the alternative models, but it would be a nice collection. He can do the primacy of particle in this stochastic process, but it's a Hamiltonian-free formulation by way of an action principle that integrates all possible paths, and it does not require microtheory. Beautiful, but as all these variational principles are, they are a bit a God's eye perspective. So the big thing is always to find the proper measure. And I mean, mathematical physics went away in that direction, but it's this nice book by Jaffe and Quinn, Quantum Physics, a Functional Integral Point of View, where sort of that gets stuck. So that's a beautiful world, but it's a world for perturbation theory. Okay, so you have to do rules. Now, Feynman was not so much an equation. I mean, Feynman is this intuitive character, so he says, I'm interested in understanding, and that the theory is not fully specified by equations, but must be completed by pictures, and there are several possible pictures. And he often goes very far in this pictorial language. So who studied Feynman's undergraduate lectures, who are not really for the undergraduates, or only for the very good undergraduates, but they have very beautiful, sometimes even a bit questionable pictures. And he thinks that this picture is an intuition pump or heuristically successful, and it helps us to understand. Yeah, this is this side, so that's not so much mathematical philosophy. You see it very often even in mathematicians who say a proof has to make us understand, and that's this tradition Feynman works on. So he isn't the nuts and bolts physics guy. He thinks that this mathematical pictorial conceptualization help us to understand. And so he draws a lot of picture. And this is, I think, the first picture. I have this from Wüttrich, where you see how he thinks through this idea. The states at a distance are unproblematic, but locally I can fill my black box with certain processes. That's what he does here. Okay, I have this process, I have this process, etc., etc. So they are localized. And you can do it according to certain rules because the Hamiltonian picture is meaningless. So you sort of supplant a micro-Hamiltonian by your rule book. And of course the question was, what were the rules? How can I build all this together? What are the possible processes, etc.? And that was not easy. Dyson comes now up with the rules. These are now the original Feynman rules. Jauch and Rohrlich. If you were interested in philosophy of simulations, that's the guy you have seen in philosophy of science. Yeah, Rohrlich, Viennese, who did some interesting philosophical papers in his 80s. Okay. So this section had, I think, two points. I wanted to show you this Dyson versus Feynman, and I wanted to show you how this action principle formulation induces a certain understanding of locality versus globality, and that supplants now, of course, the older Minkowski type. Okay, drawing theories apart has two senses, Kaiser tells us. On the one hand, we are drawing with the aid of paper tools. That's a big word in the history of science. It comes from chemistry. Yeah? These stoichiometric formulas, all these drawings of chemical bonds, these is what were paper tools. And this comes from historians of chemistry, which, but it's a general debate in history of science, and Kaiser picks it up here. And these paper tools now become the non-human centers of research networks. That's how he thinks about it. And dispersion means it was put into circulations from centers of expertise. That means where Feynman was hanging out and where Dyson was sitting, through the new post-war system of postdoctoral qualification. Okay, that's exactly like here. In those days, Stefan would like to see some postdoc, some student of Feynman come here and teach us all what are Feynman diagrams, right? Because there are so many competing uses now. People in other places use it in a different fashion, and there are the Dyson guys, and Feynman and Dyson are still hopping from position to position. So you get a network that gets nutrition and explanations from the centers, and you have the early gray literature. Yeah, so that's like the Los Alamos archive today or 10 years ago, how that worked. Kaiser's point is, well, this is important that you have your postdoc from Feynman because there's a lot of implicit knowledge here. You can't just learn it from the textbooks. So, and that you see if these Feynman diagrams hit some indigenous traditions, because a lot of that had been in the air. People had done pictorial representation because pictorial representation is quite a natural thing in mathematics. And you will see that there are sources for that also in the European tradition, terms, schemata, etc. And there were a lot of errors and missing terms. Now, I mean, errors can be just wrong, people being wrong, people forget something, people are sleepy. But you often do errors if you have a misconception, if you have your wrong mental model. And that will be, for me, a support why I think there are some representative features, because you have some mental model. I use here a concept in psychology that, apart from Ron Geary, sort of the model debate hasn't really picked up. That's by Johnson Laird. That's a pretty standard conception in learning psychology. So textbooks alone did not suffice. One needed rules of thumb far beyond the cookbook, rule-driven instructions that Dyson and managed to bundle into print, into gray literature. And the textbooks then really let you grind through stuff. You had really to calculate. I mean, these were the days where you had to calculate. This was not for axiomatic quantum field theory. Yeah, and even the later guys in axiomatic quantum field theory, they had to calculate, really grind out numbers. So, and now we have the experimentalists. So that was so far just a theoretical development. But when the textbooks are there, when pictures are there, that's interesting for experimentalists, not least because they have now a lot of stuff, a lot of measurements. They have the lamp shift, they have rubber experiments, they have Cush-Foley, so they have a lot of splitting up of energy levels that they can't explain anymore with quantum mechanics. So they throw a lot of data on their people, and they have the new big machines. The cyclotrons and then the meson factories. So Feynman diagrams were now the exchange currency with the experimentalists, and they would stay so for a long time. And that determined the appearance of the diagrams in such a way that the physical review tried to standardize the diagrams per order de Mufti, but it didn't work. So there was just a nice plurality. So you had the Cornell diagrams, the Columbia diagrams, Rochester, Chicago, Urbana-Champaign, Oxbridge, very different stuff, right? This is not yet standardized. And Kaiser makes the point that has to do because they had different experimentalists. Some did mesons, and that was, of course, way outside the Dyson rules already, because the Dyson rules let you only fundamental particles, namely electrons and photons, constitute a line, but the mesons were sort of everything between that and the proton. Okay, so in meson physics, Feynman diagrams were extended beyond the domain of Dyson's rules, which only allowed electrons and photons. So, and Chu's S-matrix program advocated even nuclear democracy. So that means there's no more fundamental particles. And he wanted to put Feynman diagrams center stage, even to axiomatize them, whatever such a black box pragmatic theory like the S-matrix theory means under that. So they clash, of course, with the quantum field theorists, apart from Princeton, where they live happily together. So in Princeton, one part does Feynman diagrams, and in the other corner, Weidmann sits. Whereas Chu says, well, everybody just has to learn S-matrix theory and forget all this quantum field theory stuff. Yeah, we are in the early 60s. Yeah, that goes all very quickly. And in the late 60s, quantum field theory is back in the game. We have the standard model, etc. We have gauge theories. We start formulating problem for normalization, and we get to normalization. But in these days, textbooks, and I'm old enough that I still have the Burke and Drell. They let you do sort of classical Feynman diagrams, and then 500 pages further, there's quantization. Okay, so they completely break out the Feynman diagrams from the Dyson rulebook. Yeah, because there's no more rulebook. We are already full in terra incognita. But these diagrams are continually used, and they are used with certain representative features in them and not just plain. And here I think is where Kaiser goes too weak. I think he says, yeah, well, look at this picture. These are just family resemblances without any meaning connecting them. So that resembles to that, that to that, that to that, that to that. But from here to there, that's already too, like a big family. It's already too far. So, but that doesn't explain to my mind why it's stuck. And also Kaiser sees, well, cannot really explain the leading role that many physicists gave to diagrams when redefining their meanings and making the break with Dyson original diagram packaging right. But now he goes, and that's still right, he says, well, there's a continuity with earlier visual representation that physicists had learned, and that's a reference point of the research tradition. So again, Latour-Volger, or probably you could add Reinberger's experimental systems to that. Yeah, and you have the bubble chamber, just as a few physicists made explicit comparisons between Feynman diagrams and Minkowski diagrams. Nevertheless, they all draw time and position axis, at least initially. Few still made the claim that what was pictured in the schematic bubble chamber reconstruction was the same thing, yet the shared visual schemata suggest some possible connection. The Feynman diagrams, most often employed beyond QED, were strikingly similar to the most heavily relied upon evidence of actual particles and the interaction. Now, of course, not the actual particles, but when they redraw it. Now you could say, well, where's the line of influence? Maybe they have the Feynman diagrams in the mind, and that's how they sort of reconceptualize what they see in the bubble chambers. And that's, of course, sort of dangerous, but it keeps you understanding. Yeah, reduction to the familiar is understanding. Some philosophers even think reduction to the familiar is even explanation, but it helps you in understanding. Of course, it's a double-edged sword, as we have seen in Maxwell's field lines, which made Maxwell search for a while for all these mechanical ether models. But there are also other traditions, and Wittrich points to them. This is before the Feynman diagrams. Yeah, people start with lists, they draw some connections, they use the quantum mechanical term schemata games for that. So there are also other pictorial traditions which you can see in the Buch-Wüttrich, that's also before Feynman diagrams. And Wüttrich, I think, rightly says, well, look, it's not just embedded in a tradition, that's sort of ex post justification, that's fine why it's disseminating. People find that familiar, they seem to understand it, fall into some traps, but he thinks, well, there's also an element of diagrammatic induction, which makes Feynman diagrams a reliable heuristic device, and it makes Feynman diagrams help to avoid certain inconsistencies. It's interesting that this is not the line, I'm not taking that line, but it's interesting that one line he doesn't take. There's this whole debate about picture proofs in mathematics. And I can imagine a lot of people that I know from philosophy of mathematics conferences who would love to see in a lot of Feynman diagram arguments some picture proofs. Yeah? So they would say, you know, this argument's probably about the Pythagoras, that you can better understand it and prove it with a picture, etc., etc. So there are some standard arguments that people use, and it's interesting nobody says that. I think that's right because the Feynman diagrams are not only a mathematical tool, right? So they are, and that will be my approach, they have this model sort of a leg in the mathematical, theoretical, physical, and in the experimental phenomena they are going to represent. I think I already told you what happened after 1970, so the S matrix goes away. We have a better justification for Feynman diagrams, strong interaction, and we have the standard model. But what continues now, despite this, is that this is mainly a boom in in theoretical physics, is that this remains the trading zone and with experimentalists, and they are very much happy. Summary of the historical part, and now afterwards I come to my own view. So the Feynman diagram stand in the tradition of visualizations. Some physicists indeed initially believed that they would capture the world more directly, from the mnemonic to the mimetic, as Kaiser put it, and from heuristic values to reification, for instance, in Chu's program, to axiomatize them. What Kaiser now does is that he, as a couple of historians of science are, he still thinks we are sort of in the days of T1, T prime, and all that boring theory focus, and he says, yeah, that's sort of weird. The philosophers just focus on theory. There's not much philosophy to me. There are paper tools and there are research traditions, and also semantic view that's still way too theoretical. So then semantic view about where models are the evolvent, the theory is the evolvent of the models. That was an approach that replaced, so to say, theory focused. So it's just traditions of pictures and paper tools. Wonderful book. There's still some philosophy for us to do after this historical book. And that's what I would like to do. So I think it's not just a matter why they stuck by constituting such a familiar reference point and a paper tool, because the bona fide errors corroborate not only Kaiser's sociological thesis of dispersion, but also indicate representative features which stood behind those errors, in the sense that physicists had formed a mental model of the process. And these representative features are changed by the increased interaction with experiments. Thus, Feynman diagrams, to my mind, have to live both in the domain of mathematics, theoretical physics, and experimental physics, and a source of corroboration, rejection, experiment in a general sense, and on the other hand of textbook pedagogy. And so my thesis will be that Feynman diagrams represent a model that has an inherent dynamic. Wüttrich goes away in that direction at basically end of the book. The central part of the pathway to the discovery of Feynman diagrams began with Feynman's representation of the quivering electron, which, according to Bright and Schrödinger, is the proper physical interpretation of the Dirac equation. Here no Dirac sees. By using his innovative representation of the electron, Feynman showed that only electrons behaving in a way that is allowed by the Dirac equation could be represented. This makes his representation a model or model system of the Dirac equation in the sense, albeit roughly, of present-day philosophy of science and Cartwright-Geary or so. Okay, his model system is sort of a bit like, you might know more in philosophy of biology, so a model organism. The fruit fly, white mice, and so the quivering electron is my model of Dirac equation, my model process, sort of like Maxwellian models, mechanical models. That's how he takes it. So, and then the Feynman diagram is a model, is a symbol system that works on that model. My model will have both legs, so it will not be just this model. Okay, so by making the model system more abstract, Feynman could now eliminate apparent contradiction, and to some extent, that's still Wüthrich, the QED phenomena that Dyson provided using his specific representation explains why there were uninterpretable divergences in the unmodified theory, while also explicating the physical content inherent in the modification of the theory. And here you see Feynman sort of playing with the diagrams, those are Feynman diagrams before Feynman diagrams. Okay, so Dyson rules explain you what works and what's not working in building up the model. So they are like building rules. And so Wüthrich says, well, it remains to be investigated to what extent Feynman diagrams are an instance of a pattern in which problems are not solved in the usual sense of the word, but are rather made to disappear by using a symbol system that appropriately represents an adequate model. Okay, I think I said this already. Well, why models? I mean, this Bohr's atomic model, 100 years old, full of internal contradiction, but we had precisely a place where we put this contradiction. These are the models where we learned electron clouds from, and of course there are no electron clouds, these are just probabilities that go to infinity. So models may contain contradictions that are justified even with stories. Stefan isn't here, but I think that's one concept he invented or contributed to the model debate in the 90s and early 2000s. And then a mathematical formalism, Bohr-Sommerfeld, and again, based on our wonder weapon principle of least action. And they can also be turned into a pedagogical model that lack core features. Yeah, these are already a pedagogical model. So is this. So this was reduced. And then they make it to the textbook. So, and Wüthrich considered Feynman diagram as a symbol system, but I will take Feynman diagrams as citizens of both worlds, and I said this already. So this is my background here. This is this models as mediator approach by Mary Morgan and Margie Morrison, which is basically characterized by 4 criteria. First, models mediate between theory, mathematics, and the empirical. They are autonomous in the explanatory function. They, in a general sense, a measuring device for certain parameters by experimental computer simulation. So you can experiment with them physically or with thought. I would say they give you some independent confirmation or disconfirmation. They help you to formulate your theory. And then there's a representation that's partly independent of the theory. They are arguing against this idea that the model is just, you know, like Snead, you have a big theory and the model is just in the logical sense a model. They are also arguing against Geary and the semantic people who say, oh, we have a bunch of model and the evolvent is called a theory because Geary has these levels of rationality. That's why I use this geometrical conception of evolvent. So it's really more and more abstract or theoretical models in Geary. So here the model is usually some real device, and the autonomy is the result of 2 components, the fact that models function in a way that's partially independent of theories, and they are constructed with a minimal reliance on high-level theories. Attention, the theory might be always there, okay? in that beautiful formal sense as you can write down a quantum field theory. You just write down a Lagrangian and then I tell you quantize it. That's a theory that's there, but in a way it's also not there because you can't do anything with it, okay? So that's why models are independent of a theory and are constructed not with well-defined limits from this theory, even if the theory is there. Yeah, and that's one of the examples, it's her beloved example, the boundary layer model, because the Navier-Stokes equations are there, but they are just too complicated to get out anything. So we have the boundary layer conception really as a model in itself that, in this picture here, connects classical hydrodynamics in the middle of the pipe. You have no friction and a boundary layer of friction only at the edges of the pipe, and you just have to see that they mathematically can live together. Yeah? So it's within a mathematical theory. You can write down Navier-Stokes equation. It's even not the most difficult stuff around. You can, what they're doing Gaching, you can add a magnetic field. So let's see whether this fulfills the criteria. Well, it's mediating between experimentalists and house theoreticians. So they are exactly doing that, basically since the 50s. So models are really the trading. It's not a model Feynman diagram. And they are also the point where the numbers parameters to be measured are specified, yeah? Because you're not measuring a single Feynman diagram, you are adding up some Feynman diagrams and then you square that and make an amplitude, and you have to know what's going in your box, right? So you decide what graphs go in your box. So your Feynman diagrams tell you what numbers you want to crunch. And autonomy has been established historically in the dissemination. This is really now an autonomous business where experimentalists and theoreticians talk to each other. However, the representation is fishy, and that's my final point. Okay, if you have a single diagram, it can be two things. It can be either, as all our CERN friends did, actually be a kind or class of processes that must be corrected by perturbations according to rules, right? They usually write simply the lowest order, and then you can add a lot of other stuff. And you say, well, I'm sort of ending at some point. And that depends how exactly I want to know it and how exactly, even more so, how far I can calculate it. So when I studied physics, I remember shocked in Trieste when they were so proud that they had done it with a computer up to 4th order, and then some Russian gave a talk, they had done it on foot to 5th order. Now I think it's the other way around. Now the computers are faster. So, or is it really a specific process with self-interaction that correspond to a mathematical expression and their function is mainly mathematical? Okay, that's the single Feynman diagram with all the connections spelled out. That has a certain probability. That's not my part, the physicists are talking. And this one by Feynman rules, or even if you don't have a Feynman rule, but this you want to associate to a propagator, to a mathematical term. So that is fine. That's what we have in the classical model debate. A model is some relation of isomorphy between the model and something, which is here a mathematical term. You see that's the math leg here. The one is the math leg. The full series is this, that's perfect. That's the physical process, but I can't get no hand at it. Okay, that's why I do this Morrison and Morgan theory, because it works well if we have a theory, but we have no idea what to do with it. Yeah, so it's unreachable by calculations. So what I'm interested in is these groups of individual terms, and such groups may be labeled by a single diagram as we had in the detectors, or they are described by certain effects. And their representative features are either motivated by a mathematical property, yeah, we go up to a certain order, or a certain effect. What does this mean? Well, they would say vacuum polarization and all such things. But here I want to show you that experimentalists are really talking in terms of such effects. Okay, so I have two things here. I have a series expansion that where every term can be by isomorphy translated into Feynman diagram. And I have the guys talking about effects. And I think the interesting point is this is a perturbation series which you can reorder according to effects. That's not trivial. This is an expansion which you can't reorder according to effects. This and this, does this correspond to something? Here it's more. These are Jou's figures. So these are two oscillations that are not in accordance to each other. So here you have certain proportions. That's better. Hydrogen atom. My hydrogen atom, the psi function, is the product of this guy, which has the Laguerre polynomials and this spherical, how's this called? Kugelflächenfunktion?
Spherical harmonics.
Spherical harmonics. Okay, these are things where you have a bunch of terms that have an index. And here, all these terms are written up. Okay, what you can do in quantum mechanics on that level is that you, of course, can associate the single term with something, namely with such a cloud picture, okay? The single term. But just imagine that you would say, well, I mean, my real atom were just probabilistic superposition of all such orbital occupations. Of course, it is not, because you see if they change, you get the light emission if one jumps from another orbital to one, and that's not the way how you treat a complex atom. But I just want to make it to you plausible that we can rearrange a series. Okay? Okay, now how spectroscopists talk. Yeah, they tell you, well, here's sort of Bohr's model, then there's Dirac, there's quantum electrodynamics, and here we have further splitting of levels. And here the next order comes. And that's how they talk, yeah? Summary of the calculation, Lamshu, they talk of a bunch of effects, yeah? They don't say first order whatever kilohertz, they say self-energy, vacuum polarization, recoil, proton size. Okay, they make sense out of a bunch of these terms in this perturbation that correspond to a certain effect they talk about. Now attention, they probably have difficulties if they won't tell you, okay, please tell me one of them and I measure you that, and please measure me that. And that's not what they can do. I guess, or only under certain conditions, how they put their measurement device. Okay. So I said, I tried to make it plausible that such a regrouping of a series can be given representative features, because at the end of the day we are physicists, so at the end of the day, if experimentalists are talking about something as an effect, we should give at least some representative feature to it. At least in the sense as models represent. Yeah, I don't say this effect is there. Basically, all the effects that were around in 1900 have been given deep explanations. Stark effect, anomalous Feynman effect is the normal quantum mechanical normality, etc., etc. Yeah? So I'm not going Cartwright, I'm not going, oh, physics is a world of effects. That's not what I'm doing. But on the other hand, we shouldn't let the effects just be something that has no representative features. Okay, so that's why I think my take is more general than Wüttrich's model systems. Models partake here both in the physical and mathematical realm, not just a model system in the same instrumental vein as a model organism. Okay, it's not that We've just chosen to work with the fruit fly because it's practical. And such a unified approach seems to me to be more adequate to the double nature of that Feynman diagrams have now as a mediator between the experimentalists and the theoreticians, and really mediating to deep mathematical facts, that some of which are unresolved. Yeah? So I don't say Rüthi is wrong with this quivering electron as a model in the early days, but we have a lot of effect things that are not anymore models of some physical processes. It's just something the physicists were talking about. Okay, and the price was, of course, that we get a rather complicated nature of what Feynman diagrams represent. Now, a final thing that's one outlook, that I think what Kaiser now shows us that models are not static. Yeah, and models, that's a kind of an appendix. Models are constantly rearranged for various purposes and experimented with. Rules are initially expertise, so it's implicit knowledge. That's fine what Kaiser says. But I mean, you have, if you get your postdoc, you have to be able to communicate it. It's not this Polanyi real guy. I mean, I really studied high energy physics practicum with such a guy who didn't say a word with his screwdriver and our NIM electronic, and I didn't learn anything with him. So, you know, if you plug the cables, you have to plug the cables properly not to refute Einstein's relativity theory. So that's not trivial, but that guy never said anything. So that guy for me is the ideal of communicable knowledge. So you need that this way of talking about Feynman diagrams can be transferred into sort of Hartmannian stories. And these stories might be more general or contain representative features, because we are often going far outside the realm of Dyson. And here's something which you can learn. Unfortunately, the picture isn't nice. That's how didactics people talk about. I try to make sense for the model debate of what these educational scientists tell us. I mean, here you have always intermediate model, and you can say, well, there's a didactical target model, and the didactical target model isn't, of course, the model that works as a heuristic device for the physicist. This would be a different one. And of course, the story will be a different one for that target model. And that's why here the didactics people have no error between the target model of the didactics and of the expert consensus model. Okay, and I think I finally should end with a picture for the real Bavarians about some complicated processes, how to get your beer. Thank you.